Welcome to Systemic Stack. My name is Kabir Anand. This is episode 22 of the System Engineering series, and today we will explore retry patterns in a way that helps you prepare for system engineering interviews on this topic. In a distributed world, network noise and database locks are inevitable, so mastering how your system recovers is a huge green flag for interviewers. We look at 7 core strategies, including exponential backoff and jitter, to ensure you can build resilient communication without accidentally triggering a retry storm. It's about moving beyond basic oops to production-grade stability. We begin with the fundamental chaos of distributed systems, specifically focusing on how to distinguish between two categories of errors, transient blips and permanent failures. This distinction is crucial because it tells us exactly when a retry is helpful and when it's just wasting resources. From there, we look at the immediate retry approach and the risks of triggering a retry storm that could crash a struggling service. To solve that, we explore 2 core strategies, exponential backoff and jitter. You will see how these work together to prevent thundering hertz and keep traffic flow manageable. We'll also tackle the constraints of latency budgets and how combining retries with circuit breakers provides a necessary safety valve. Well, it's also important to cover what happens when retries actually fail, so we'll look at dead letter queues and the essential role of idempotency in keeping your data consistent. By the end, you'll have a clear framework for building resilient communication, which is exactly the kind of depth interviewers are looking for when they ask about system reliability. Let's set the scene with a situation you'll likely encounter. Imagine you're operating a high-traffic microservices architecture where services are making thousands of requests per second. Suddenly, a downstream database experiences a minor 2-second lag. If your services aren't using smart retry patterns, they might immediately surface errors to the user. Or even worse, they might all try to hit the database again the exact millisecond it recovers, knocking it right back down. What matters here is that at scale, small constraints like connection pool limits and network congestion become major bottlenecks. The failure mode here isn't just a single error, it's a cascading failure across your entire fleet. In an interview, explaining this context shows you understand that your code doesn't live in a vacuum. You're demonstrating that you know how to protect the system's stability while still trying to provide a seamless experience for the user. It's all about finding that balance between being persistent enough to succeed and being polite enough not to overwhelm your dependencies. Mastering retry patterns is about more than just a simple loop. It's about designing for resiliency. It works by intercepting exceptions from remote calls and deciding based on the error type whether to wait and try again. What matters here is that network reliability is essentially a myth in cloud environments. You have to assume that every call could fail. The primary failure mode here is over-optimism, assuming that if you just try again enough times, it will eventually work. This can lead to resource exhaustion, where your application spends all its time retrying dead requests rather than serving new ones. In a system design interview, you want to show that you've thought about the trade-offs of these patterns. You aren't just adding retries to be safe, you're doing it with specific limits and guardrails. It's about building a system that can gracefully handle the unhappy part just as well as it handles the successful one, ensuring that transient issues stay transient instead of becoming permanent outages for your users. In a world of microservices, chaos is the only constant. We're talking about temporary network blips, database locks, and downstream service reboots that are completely inevitable. These events work as noise in your system, and how you handle that noise determines your overall uptime. What matters here is that if every minor interruption triggers a high-severity alert, your team will burn out and your users will lose trust. However, the failure mode to watch for here is amplification. If your retry logic is too aggressive, it can turn a tiny blip into a total system collapse. One simple way to picture this is a feedback loop in an audio system. A small sound gets amplified until it's a deafening roar. In an interview, when you're asked about service communication, bringing up this chaos shows you're a realist. You're acknowledging that the network is unreliable and that you've built your architecture to absorb these shocks rather than letting them pass through to the end user. It's about creating a buffer that keeps the system stable under pressure. A critical part of any retry strategy is distinguishing between transient and permanent errors. Transient errors like a 503 service unavailable or a 429 too many requests are temporary issues where a retry actually makes sense because the situation might change in a few milliseconds. Permanent errors like a 404 not found or 401 unauthorized will never succeed no matter how many times you try. Retrying a 401 is just a waste of compute and time. What matters here is that it saves your system from spinning its wheels on problems that require a code change or human intervention. The failure mode here is misclassification. If you treat a permanent error as transient, you're just adding unnecessary latency and load to your system. In an interview, you should mention that your retry logic always inspects the error code first. This shows you're thinking about the cost of each retry and that you're prioritizing system efficiency. It's a key sign of a senior level understanding of how distributed systems actually behave under stress, Now, the simplest approach is the immediate retry mechanism. It works by having the client resubmit a failed request the very moment it receives an error, with no delay at all. It's effective for those incredibly brief sub-millisecond network glitches that happen occasionally. It matters because it offers the lowest possible latency for a successful recovery. Well, the downside is that it's extremely risky. The major failure mode is that it's incredibly aggressive. If the downstream service is already struggling with load, hitting it again immediately is the worst thing you can do. You are effectively kicking someone while they're down. From an architectural perspective, this is often too blunt an instrument for modern high-scale systems. In an interview, you'd explain that while you might start with this for very specific low-risk calls, you generally want something more controlled. It's important to justify why this simple approach might be insufficient and what better alternatives you'd consider to protect the health of the broader ecosystem of services. When immediate retries go wrong, you get a retry storm. This works as a massive synchronized wave of traffic where every client hits the failing service simultaneously. It matters because this can turn a minor slowdown into a total outage, creating a self-inflicted denial of service attack. The failure mode here is a complete system collapse. Instead of just one service being slow, every service that calls it starts to time out because they're all stuck in a loop of failed retries. In an interview, you'll want to describe this as a thundering herd on steroids. It's a perfect example of how local optimizations trying to make your one request succeed can lead to global failures. The trade-off is between individual request success and the stability of the entire platform. When you're designing these systems, you have to be a good citizen and realize that being too persistent can actually be destructive. Explaining this risk shows you have the architectural foresight to avoid building systems that accidentally destroy themselves when things get a little bit bumpy. To avoid those storms, we use exponential backoff. Instead of hammering a service, we increase the delay between each attempt. This works by giving the failing service more and more time to recover as we continue to fail. It matters because it effectively throttles the traffic, allowing the downstream system to clear its queue and get back on its feet. However, a failure mode here is increased user latency. If you back off too far, the user might be waiting seconds for a response that should have taken milliseconds. You're trading off a quick error for a slow success. In an interview, this is a great place to talk about the balance of system health and user experience. You're showing that you know how to give a struggling dependency some breathing room. It's a much more sophisticated way to handle failure than just trying again as fast as possible. By spreading out the load over time, you significantly increase the chances that your later retries will actually land when the service is ready. The Backoff algorithm usually follows a formula like delay equals a base time multiplied by 2 to the power of the attempt number. So if your base is 100 ms, your sequence is 100, 200, 400 and so on. This works by creating an expanding window of time between requests. It matters because it provides a predictable mathematical way to scale back your regression. But there's a failure mode. You have to cap the maximum delay. Without a limit, the wait times could eventually reach minutes, which is useless for a real-time app. When you're explaining this in an interview, be sure to mention the importance of a max backoff ceiling. You also need to think about how to choose that initial base value. Too small and you're still too aggressive, too large and you're making the system feel slow. It's a fine-tuning process that depends on your specific service level objectives. Showing that you understand the math and the practical limits of this algorithm signals that you're ready to implement this in a real production environment. Even with Backoff, you can still face the thundering herd if all your clients are perfectly synchronized. If 1,000 clients fail at the same time and use the same formula, they'll all retry at the exact same 100 ms mark, then the 200 ms mark, and so on. This works as a series of massive pulses that can still crash a server. The solution is jitter, which is just adding some randomness to the delay. Instead of exactly 100 ms, maybe one client waits 95 ms and another waits 105 ms. What matters here is that it breaks that synchronization, turning those pulses into a steady, manageable flow of traffic. The failure mode here is using a poor random distribution that doesn't actually spread the load. In an interview, bringing up jitter is a massive green flag. It shows you've thought about how your code behaves when it's running on thousands of machines at once. It's about moving from a single client mindset to a total system mindset, which is exactly what senior engineers are expected to do in high-scale environments. We also have to consider latency budgets and timeouts. Every request has a total time it's allowed to take. This works by setting an overall limit for the entire operation, including all its retries. It matters because if your total retry time exceeds the calling service's timeout, you're just wasting work on a request that has already been abandoned by the user. A major failure mode is zombie requests, where your retry loop keeps running long after the caller has given up and moved on. This clogs up your threads and resources for no reason. In an interview, you should talk about how you coordinate these timeouts across the entire call chain. You want to fail fast if you know you're going to exceed your budget anyway. It's about being efficient with your resources and recognizing when an operation is a lost cause. This prevents a single slow dependency from causing a backup that affects every other part of your service, which is a key part of maintaining overall system throughput. For even better protection, we integrate circuit breakers with our retries. While retries say, try again, circuit breakers say, stop trying entirely for a while. This works by tracking the failure rate. If it gets too high, the circuit opens and all requests fail immediately without even trying the downstream call. It matters because it gives a failing service total relief, which is often the only way it can truly recover from a massive overload. The failure mode to watch for is a misconfigured threshold where the circuit opens too easily or stays open too long, causing unnecessary downtime. In an interview, explain how these two patterns complement each other. Retries handle the small transient blips while the circuit breaker handles the sustained outages. This dual-layered defense is a hallmark of a robust architecture. It shows you're not just hoping things work. You've built a system that can actively protect itself and its neighbors when things go south, which is exactly what a resilient distributed system needs to do. So, what happens when you've exhausted all your retries and the circuit breaker is still open? This is where dead letter queue or DLQ escalation comes in. It works by taking that failed request and moving it to a separate storage area for later processing or manual inspection. What matters here is that it ensures that even when things are broken, you don't just lose data. The failure mode here is silent failure, where nobody is actually monitoring the DLQ and it just fills up until it crashes the queuing system. In an interview, you should describe this as an ultimate safety net. It allows the system to admit defeat on a specific request without losing the user's intent. You might have a background worker try it again an hour later, or an engineer might look at it to see if it was a malformed payload. By offloading these failures, you keep your main processing pipelines clear and responsive. It's a critical part of building an auditable, reliable system that can handle the worst-case scenarios gracefully. You absolutely cannot talk about retries without talking about idempotency. It's the absolute rule for safe retry execution. It works by ensuring that doing the same thing multiple times has the same effect as doing it once. What matters here is that if a call succeeds on the server but the response is lost on the network, the client will retry. If that's a payment call, you don't want to bill the customer twice, right? The major failure mode is retrying a non-idempotent operation, which leads to duplicate data and corrupted state. In an interview, you must mention idempotency keys, unique IDs the server uses to recognize a duplicate request and return the cached result instead of reprocessing it. This is the safety mechanism that makes all our other retry strategies possible. Without it, retries are actually dangerous. Showing you understand this risk is a huge signal to an interviewer that you're a senior engineer who cares about data integrity just as much as you care about system availability. When you're answering an interview question about reliability, you want to show you have a complete framework. Interviewers aren't just looking for the word retry. They want to hear about 5 main things: identifying transient errors, using exponential backoff, adding jitter, respecting latency budgets, and ensuring idempotency. A strong answer will also mention circuit breakers as a way to protect the downstream service. You're signaling that you understand the trade-offs, that retries improve availability but increase load and latency. A classic failure mode in these interviews is suggesting infinite retries. Avoid that at all costs. Instead, talk about your limits and what happens when those limits are hit, like using a dead letter queue. By covering these points, you show you've dealt with these issues in production and that you're prepared to handle the messy, unpredictable nature of real-world distributed systems. It's about demonstrating that you can build a system that is both persistent and safe, which is exactly what companies are looking for in their senior talent. So, we've wrapped up how to handle those inevitable blips in distributed systems. The mental model here is all about balancing persistence with politeness. We covered three core strategies: immediate retries for quick fixes, exponential backoff to give services room to breathe, and jitter to break up those dangerous thundering herd traffic spikes. In a design interview, you've got to show you understand the trade-offs. Sure, retries build resilience, but without idempotency and strict retry limits, you're just risking a serious attack. By layering in circuit breakers and dead letter queues for the persistent failures, you're not just blindly hammering a server, you're building a sophisticated recovery loop. That's the difference between a brittle system and one that's truly production ready. That's a wrap on episode 22. We've covered why building resilient communication means balancing retries with safety. For your next system design interview, remember that a simple retry whoop isn't enough. You'll want to demonstrate how you manage the 7 core elements: immediate retries, exponential backoff, jitter, retry limits, circuit breakers, idempotency, and dead letter queues. Explaining how these prevent cascading failures shows you've got a handle on real-world bottlenecks. If you're finding this useful, hit subscribe to keep leveling up. In the next episode, we will discuss leader election, where we'll discuss situation, core understanding, purpose. Good luck with your preparation, and I'll see you there.